And inside it, in one of its most active star-forming regions, the Tarantula burns. When astronomers measured the size of the Tarantula Nebula, the numbers are hard to process. The nebula spans approximately 1,000 light years. 1,000. The distance light travels in 1,000 years. For context, the Orion Nebula, the most famous nebula visible from the northern hemisphere, the one in Orion's sword that you might have pointed out on a camping trip, is about 24 light years across. The Tarantula Nebula is 40 times larger in terms of actual physical size. And if you were to measure the mass of gas and dust in the tarantula, all the material available to form stars, the estimates suggest it contains enough material to form approximately 450,000 times the mass of our sun. Not 450,000 suns, 450,000 times the mass of the sun in raw star-forming material. This is not a place where a few hundred stars are forming. This is a place where the universe is manufacturing stars on an industrial scale, a factory, the most active star factory in our cosmic neighborhood, perhaps the most active in the entire local group of galaxies. I remember when I first really sat with those numbers. I had read them before, in books, in articles, but there is a difference between reading a number and letting it settle 1,000 light years across. I tried to visualize it. I tried to find an analogy, and I couldn't. There is no analogy. The numbers for astronomical objects exist outside the range of human intuition. We have not evolved to feel the difference between 1,000 light years and 1,000,000. They're both simply incomprehensibly large. And so what I found helps is let go of trying to understand the size and instead let myself feel the response to the images, to the light itself. That light left the Tarantula Nebula 170,000 years ago. When it left, modern humans were just beginning to migrate out of Africa. The first cave paintings were still tens of thousands of years in the future. Every civilization, every empire, every invention, every war, every birth and death in the entire history of human culture happened during the journey of that light, from there to here. The light that lets us see the tarantula has been traveling since before language. The heart of violence, R136, the most extreme star cluster known. At the center of the Tarantula Nebula, at the very heart of all that gas and chaos, is a star cluster. It is called R136, and it is one of the most extreme places in the known universe. R136 is a compact cluster of young, massive stars packed into a region only about 35 light years across. Inside that region, an area that would fit inside the distance from Earth to its nearest stellar neighbor, are some of the most luminous, most massive, and most energetic stars ever discovered. The density of stars in the core of R136 is approximately 3,000 times higher than in the solar neighborhood where we live. 3,000 times more stars per unit volume. If we lived in R136, our night sky would be filled with stars so bright that the night would never be truly dark. Stars bright enough to cast shadows. A sky so full of light that the concept of darkness, the quiet, dark nights we associate with sleep and rest and the turning inward of the mind, would simply not exist. The most massive star known in R136, and arguably one of the most massive stars ever discovered, is called R13601. It has a mass approximately 215 times that of our Sun, 215 solar masses. Our Sun is already so large that 1,000,000 Earths could fit inside it. R136A1 has a mass 215 times larger than that. It is not the physically largest star known. Some red supergiants are physically larger in terms of volume, but in terms of mass, the sheer amount of material packed into a single star, R136A1, is in a category of its own, and its luminosity matches its mass. R136A1 is approximately 8.7 million times more luminous than the Sun, 8,7 million times. If it were where the Sun is, it would appear in the sky not as a point of light but as a blazing disk, and its radiation would have stripped the Earth's atmosphere in short order. There would be no life. Nothing could survive in close proximity to this object. It is not a star in the comfortable, life-giving sense our Sun is. It is something else, something almost beyond categorization, a fusion reactor operating at the absolute limit of what the laws of physics allow. Stars like R136A1, called Wolf-Rayet stars, or O-type supergiants, burn so intensely that they're blowing themselves apart. The radiation pressure from inside the star, the pressure of the light itself, pushing outward, is so enormous that it overcomes the gravitational force trying to hold the star together. The result: the star drives a stellar wind. Not the gentle solar wind. Our Sun produces a flow of charged particles that streams outward at a few hundred kilometers per second. The stellar wind from R136A1 moves at approximately 2,500 kilometers per second, and it carries away mass equivalent to the entire mass of the Earth every few months. Every few months, the mass of our entire planet carried away as wind. This star is destroying itself, radiating so intensely, blowing away so much mass that its lifetime is measured not in billions of years like our Sun, but in millions, perhaps just a few million years. In stellar terms, a brief, violent, blazing life, a life lived at maximum intensity, until the fuel runs out and the star dies in an explosion that will outshine the entire galaxy. I think about what it means that a star can live this way. Our Sun has been burning for 4.6 billion years. It will burn for another 5 billion, steady, reliable, constant. It is the kind of star that allows a planet to develop life, because life takes time. Life takes stability. Life needs a star that keeps the same temperature and brightness for billions of years, while chemistry slowly, patiently works toward complexity. Stars like R136A1 have nothing to do with life. They are not stable. They are not patient. They are fire without restraint. They are what happens when gravity assembles more material than the resulting star can calmly hold. And they live and die so fast that no planet could form around them. No chemistry could begin. No life could arise. They blaze. They explode. They are gone. And the universe doesn't mourn them. It simply uses their remains, the heavy elements forged in their cores and scattered by their explosions, as raw material for the next generation of stars. More modest stars, quieter stars, stars that can hold a planet close for long enough for something to notice. R136 contains many such stars, not just R136A1. The cluster contains dozens of stars with masses exceeding 100 times that of the Sun. Some estimates suggest the cluster may contain stars with masses up to 300 solar masses, right at the theoretical maximum for how massive a star can be before the radiation pressure overwhelms gravity during formation. The upper mass limit for stars, the edge of what physics allows. R136 is pushing against that edge. Star after star, packed together, each one pouring radiation and stellar wind into the surrounding nebula, ionizing the gas, heating it, pushing it outward, compressing it in other places, and triggering the formation of yet more stars. The cluster is both destroying and creating. Its radiation is slowly dispersing the nebula around it, blowing the raw material away, eventually ending the star formation. But as it does so, the compressed shells of gas at the edges are collapsing under their own gravity. New stars, triggered by the violence of the old ones. Creation from destruction. The cycle. The ultraviolet radiation from R136 is so intense that it can be detected across the entire Large Magellanic Cloud. It dominates the ultraviolet sky of that galaxy the way our sun dominates our sky. If you were on a planet, if a planet could somehow exist in the Tarantula Nebula, which is unlikely given the violence of the environment, and you look toward R136, you would see something no human eye has ever seen. A cluster of hundreds of blazing blue-white stars, packed so close together they would appear to the naked eye as a single object brighter than anything else in the sky. Brighter than the full moon, bright enough to read by, in a sky that was never fully dark, surrounded by the pink and red glow of ionized hydrogen. The nebula itself lit from within by the cluster's light, stretching across the sky in every direction. The entire sky glowing, alive with light, a sky nothing like ours, nothing like any sky any living thing has ever seen. The making of stars, how suns are born in the tarantula. Let me tell you how a star is born. Not the textbook version, the felt version, the version that, when I understood it properly for the first time, made me feel something shift. Imagine a cloud. Not the clouds above you right now, not the water droplets and ice crystals of Earth's weather system. A molecular cloud, an enormous, cold, dark cloud of hydrogen gas and dust drifting through space. Temperature, perhaps 10 to 30 degrees above absolute zero. Cold enough that the hydrogen is in molecular form paired atoms, moving slowly, weakly bound. From the outside, it would look dark. Almost nothing, a shadow against the stars, a region of the sky where the stars seem to disappear, because the dust in the cloud is absorbing and scattering the light of the stars behind it. This darkness is where everything begins. The cloud drifts. For millions of years, nothing happens. It drifts through the galaxy, encountering other clouds, sweeping up material, slowly growing, or it encounters a disturbance, the shockwave from a nearby supernova, the gravitational influence of a spiral arm, the tidal forces of a passing cloud. The disturbance matters because molecular clouds can drift for a very long time without forming stars. They need a push, a trigger, something to start the process of collapse. In the Tarantula Nebula, the triggers are everywhere. The radiation and stellar winds from the massive stars already formed the stars of R136, and the other clusters within the nebula push into the surrounding gas. They create shells, expanding bubbles of hot, compressed gas surrounding each cluster. And at the edges of those bubbles, where the expanding shell meets the cold molecular gas beyond the gas, is compressed, squeezed, more denser, and when the density in a region becomes high enough, gravity takes over. The region begins to collapse under its own weight. It falls inward, slowly at first, then faster. The collapse converts gravitational potential energy into heat. The center of the collapsing cloud warms hundreds of degrees, then thousands, then tens of thousands, And somewhere in the process, when the temperature and pressure at the center reach the threshold, hydrogen nuclei begin to fuse, protons colliding with enough energy to overcome their electromagnetic repulsion, fusing, releasing energy. The energy that was locked in the hydrogen nucleus, binding energy, released as light and heat. The light pushes outward, balancing gravity, stopping the collapse. A star burning where before there was nothing, just cold gas, just darkness. This process is happening throughout the Tarantula Nebula, not in one place, everywhere, in hundreds of regions simultaneously. The nebula is alive with the births of stars, some of them just beginning to collapse, still invisible behind the cloud, some of them in the process of ignition, the protostar phase, when the central mass is hot and contracting, but nuclear fusion hasn't begun yet. Some of them just switched on newborns, blasting away the remaining cocoon of gas and dust with the first stellar wind emerging into the visible light spectrum for the first time. Some of them already weeks or months old by stellar standards, already influencing the gas around them, already shaping the cloud. The tarantula is a nursery, not a quiet nursery. A nursery during the loudest, most chaotic night. A nursery where the newborns are not small and fragile, but enormous and violent. Where the act of birth reshapes the environment. Where each new star changes the conditions for the next. Astronomers use the term starburst for regions like the Tarantula Nebula, a starburst region, a place where the rate of star formation is dramatically, sometimes orders of magnitude higher than in typical parts of a galaxy. In the Milky Way, the typical rate of star formation is about 1 to 3 solar masses per year. In the Tarantula Nebula, the rate of star formation in just this one region may be 20 to 100 times higher. The universe forming stars here with an urgency, an intensity, a pace that has no equivalent in our own galaxy. Why here? What makes the Large Magellanic Cloud and the Tarantula in particular such a hotbed of star formation? Several factors. The gas in the Large Magellanic Cloud has a lower metallicity than the Milky Way. It contains fewer heavy elements. Counterintuitively, this can promote star formation. Heavy elements help cool gas more efficiently, and cooler gas forms different kinds of stars. The LMC is also being gravitationally stirred by its interaction with the Milky Way and the Small Magellanic Cloud. The tidal force is compressing gas in some regions, triggering collapse. And there's a feature called the 30 Doradus complex, the region in which the tarantula sits, that appears to be fed by inflowing gas streams, continuously supplied with fresh material, a star factory with a continuous supply chain. I want to pause here for a moment, because I've been describing this in terms of physics, of gas and gravity and compression and ignition, and all of that is true. But there is something else happening when I think about the Tarantula Nebula that I find hard to put into pure scientific language. There is something about the scale of creation that is, and I don't use this word lightly, moving. We use the word birth for stars. We talk about stellar nurseries. We talk about the universe as if it is alive in some way. And I don't mean that literally. I don't mean the universe is conscious or purposeful or caring. But I mean that the processes, the vast automatic physical processes, produce something that resembles what we recognize as creativity. New things that didn't exist before, complex things that change the environment around them, stars that will warm planets, stars that will forge elements, stars that will eventually die and scatter those elements, the iron, the carbon, the oxygen, the calcium into the next generation of clouds, into the next generation of stars, into the next generation of planets, into the molecules of the next generation of life. The Tarantula Nebula is not just making stars, it is making the future. In the most literal possible sense, the supernova next door, SN 1987A, and the day the universe knocked on the 23rd of February 1987, something happened that changed astronomy. At 7:35 a.m. Universal Time, a burst of neutrinos, tiny, almost massless particles that travel at nearly the speed of light and pass through ordinary matter almost without interacting, arrived at detectors buried deep underground in Japan, the United States, and the Soviet Union. Thousands of neutrinos in a few seconds, where normally you might detect a handful in an entire day. A flood, Impulse. The detectors registered something they had never seen before. A few hours later, astronomers around the world began reporting a new bright object in the Large Magellanic Cloud, where before there had been a relatively unremarkable blue supergiant star, a star called Sangelik, negative 69 degrees 202. There was now a naked eye visible explosion, a supernova, in our galactic neighborhood, the closest supernova observed since 1604. It was named SN 1987A, and it was happening just 168,000 light years away, on the outskirts of the Tarantula Nebula. This moment, the 23rd of February 1987, is one of the most significant days in modern astronomy, because for the first time, we didn't just see a supernova, we felt it. The neutrinos arrived before the light because neutrinos barely interact with matter. They passed right through the dying star while the light was still trapped inside. They arrived at Earth hours before the optical brightening was visible. We detected the death of a star in the neutrino channel, a kind of astronomy that had only been theoretical until that moment became real. We caught a star dying in real time at close enough range to detect the invisible particles that carry most of the energy of a stellar collapse. The universe knocked on the door. We opened it. SN 1987A became the most studied supernova in history. Thousands of scientific papers, observations across every wavelength radio, infrared, optical, ultraviolet, X-ray, ground-based telescopes, space telescopes, neutrino detectors, gravitational considerations. Everything pointed at one place, one dying star, 168,000 light years away. What we learned confirmed and refined our models of how massive stars end their lives. The core collapses in less than a second. The outer layers fall inward, bounce off the impossibly dense collapsed core, and explode outward. Heavy elements forged in the final moments of the star's life and in the explosion itself scattered into space, including radioactive nickel 5-6, which decays to cobalt and then to iron, and the gamma rays from that decay were detected from SN 1987A, confirming that supernovae are iron factories. Every iron atom on Earth was made in an explosion like this one, possibly in explosions in the Tarantula Nebula itself, in explosions that happened before our solar system existed. Today, 37 years after the explosion, SN 1987A continues to evolve. The expanding shell of debris moving outward at about 7,000 kilometers per second has been colliding with rings of gas that the star expelled in the tens of thousands of years before it exploded. The collision is heating the rings, making them glow, creating a light show that has been brightening and evolving over decades. A stellar death that we have watched in real time for nearly 4 decades. And in the coming years, perhaps in your lifetime, a new object may appear in the center of the expanding debris. A pulsar, the collapsed core of the original star, spinning hundreds of times per second, sending out pulses of radiation, the star's heartbeat still going long after the star itself is gone. There is something I find almost unbearably poignant about SN 1987A. The star Sandy Leak, negative 69 degrees 202, existed for about 20 million years. It burned, it evolved, it shed its outer layers, it collapsed, it exploded, and it did all of this 168,000 years ago. The light of its death reached us in 1987. We weren't there when it happened. We arrived at the scene 168,000 years late. And yet, thanks to the neutrinos and the expanding light echo and the decades of follow-up observations, we have been able to reconstruct the event with extraordinary precision. We know what the star looked like. We know how it died. We know what it left behind. We are forensic scientists, working a case 168,000 years cold, and somehow because of light, because of physics, because of the consistency of natural law, we can still solve it. What the James Webb saw, new eyes on the oldest story. In 2022, the James Webb Space Telescope, the most powerful astronomical observatory ever built, turned its 6.5-meter gold-coated mirror toward the Tarantula Nebula. What came back changed everything. Not the basic science, but the detail, the resolution, the depth. Where previous telescopes had seen a glowing cloud of gas with some structure, Webb showed a world of extraordinary complexity. Pillars of gas and dust lit from within by newly forming stars, with the most massive ones blasting cavities in the surrounding material with their stellar winds. Thousands of individual stars, young, hot, bright, that had been invisible behind the dust in previous observations. Stars still embedded in their birth cocoons of gas, only detectable in infrared because infrared light penetrates dust that blocks visible light. And at the edges of the nebula, beyond the chaos of the central star-forming region, distant background galaxies, hundreds of millions of light years away, visible through gaps in the gas. The Tarantula Nebula, seen through James Webb, is not a cloud. It is a landscape, a three-dimensional world of pillars and cavities and sheets of gas and individual stars at every stage of life. The Webb images of the Tarantula Nebula are, I think, among the most beautiful things ever made by human technology. Not just scientifically, aesthetically. The combination of the infrared sensitivity and the resolution creates images that feel like looking at a painting, but a painting made of actual light from actual objects 170,000 light years away. The colors in the processed images are false. They represent different infrared wavelengths translated into colors our eyes can see, but they are not arbitrary. Each color represents a specific emission from a specific element or molecule. The orange is hot carbon compounds, polycyclic aromatic hydrocarbons glowing at the edges of gas clouds. The blue-white is ionized oxygen gas stripped of electrons by the ultraviolet light of young stars. The red is hydrogen. The white points are the stars themselves. Every color is a chemical signature. Every color is telling you what is happening in that part of the cloud. Looking at the Webb images of the tarantula is not just beautiful. It is reading. One of the most striking features visible in the web images is the structure at the edges of the nebula. They're far from the blazing core of R136, sheltered from the worst of the ultraviolet radiation, are the pillars, towers of gas and dust, dozens of light years tall, the tips pointing toward the central cluster like fingers pointing at a fire. The tips are being eroded. The ultraviolet radiation and stellar wind from R136 is slowly eating away at them, eating away at the cooler, denser gas. But inside the densest regions of those pillars, shielded by the surrounding material star formation, is still happening. New stars, protected by the very material that is being destroyed to reveal them. And at the very tips of the pillars, where the erosion is most advanced, where individual globules of dense gas are being separated from the main structure, are what astronomers call proplets, protoplanetary disks of gas and dust around young stars, the raw material for planets, caught in the act of being assembled, in the most violent region of the local universe. Even here, even in the face of all that radiation, even in the shadow of R136, the machinery of world-making continues. I find that profoundly, I don't know how else to say this, hopeful. Not hopeful in a naive way, not hopeful because things always work out, but hopeful in the sense that the universe's tendency to create complexity, to form structure, to build stars from gas and planets from disks and chemistry from chaos is not easily stopped, even in the most violent environment in our cosmic neighborhood. Even being blasted by the radiation of a star 8 million times brighter than the sun. Even in the middle of a starburst region, the disk forms, the planet begins. Not all of them will survive. Most probably won't. The radiation is too intense, the stellar winds too strong. Most of those protoplanetary disks would be stripped away before planets can fully form, but not all. Some, perhaps, in the sheltered corners, in the shielded edges. Something might persist, something might begin. The elements we are made of, how the tarantula forges the universe, everything you are made of was forged in a star. You have heard this before. It is one of those facts that everyone knows. In the way everyone knows the Earth orbits the sun as an abstraction, but I want to make it concrete tonight. I want to trace the specific journey, the hydrogen in your body, the hydrogen that is part of every water molecule in your cells, every organic compound in your DNA, every reaction happening in your body right now. That hydrogen is primordial. It was made in the Big Bang 13.8 billion years ago, in the first few minutes of the universe, when temperatures were high enough for protons and neutrons to fuse. The hydrogen in your body is as old as the universe. It has been part of nebulae, part of stars, part of oceans, part of living things. It has been you, and before you, something else. And before that, something else still, all the way back to the hot plasma of the early universe. You are carrying the oldest thing there is. In the water in your cells, the carbon in your body, carbon, the basis of all organic chemistry, the element that forms the backbone of proteins and DNA, the element without which life as we know it could not exist. Carbon is not primordial. It was not made in the Big Bang. It was made inside stars, specifically in a reaction discovered by astronomer Fred Hoyle in 1954, the triple alpha process. Two helium nuclei fuse to form beryllium. Beryllium, before it can decay, captures a third helium nucleus. The result, carbon 1, 2, Hoyle noticed that this reaction could only work at a very specific energy level, that carbon-12 had to have a resonance state at just the right energy for the reaction to proceed. Without that resonance, carbon wouldn't form in stars. And without carbon, life as we know it couldn't exist. He predicted the existence of that resonance before it was measured. He was right. The universe is fine-tuned, or at least it has the properties to allow carbon to form in stellar cores. Whether that is coincidence or something deeper is a question beyond the reach of science. But the carbon in your body was forged inside stars. Stars that died before the sun was born. Stars perhaps not unlike the ones forming in the Tarantula Nebula right now. The oxygen you are breathing, oxygen is also made in stars more massive than the sun through a process called oxygen burning in the later stages of stellar evolution, when the star is running out of carbon and neon diffuse. For a relatively brief period, massive stars fuse oxygen, producing silicon and sulfur. And at the end of that phase, when the oxygen is exhausted, the star moves toward its final moments. The oxygen made in that process is blown into space when the star dies, either in the winds of a giant star or in the violence of a supernova, and scattered into the galaxy, where it mixes with other gas and eventually finds its way into a new molecular cloud and collapses into a new star with planets, one of which by extraordinary fortune develops an ocean and an atmosphere and life, and you breathing the iron in your blood. Iron, the element at the end of the line, the end of stellar nucleosynthesis. Stars fuse elements up the periodic table, each stage releasing energy, hydrogen to helium, helium to carbon, carbon to oxygen, and so on through neon, sodium, magnesium, silicon, sulfur, up to iron. Iron is the end point. Fusing iron consumes energy rather than releasing it. When a star builds an iron core, fusion stops. Gravity wins. The core collapses in a fraction of a second. The resulting explosion, the supernova, is how iron is distributed into the galaxy. The iron in your hemoglobin, the iron that carries oxygen through your blood, the iron that keeps you alive, was made in the final moments of a dying star, released in its death, scattered through space, eventually incorporated into the solar nebula from which the Earth formed, eventually concentrated in the Earth's crust, eventually absorbed by the first photosynthetic bacteria, eventually finding its way through 4 billion years of biological evolution into you, into the blood that is moving through your body right now. As you breathe, as you rest, carrying the legacy of a star's death with every heartbeat. The stars forming in the Tarantula Nebula right now are participating in this cycle. The most massive of them will burn for only a few million years before exploding. When they do, they will scatter their contents, the carbon, the oxygen, the iron, the heavier elements made in the explosion itself, into the gas of the Large Magellanic Cloud, into the next generation of molecular clouds, into the next generation of stars, perhaps into planets, perhaps into chemistry, perhaps into life 170,000 light years away from us. We will never know. We will never be there to see it. But the process will continue, the same process that made us, the same chain continuing elsewhere, the architecture of chaos, how violence creates structure. The Tarantula Nebula looks chaotic. In the raw images and even in the processed color-coded web images. It looks like an explosion in slow motion. Gas billowing outward, pillars being eroded, stars blasting cavities in the surrounding material. Nothing orderly, nothing like the clean diagrams in textbooks. And yet, look longer. Look at the large scale. There is architecture here. There is structure. The central cluster R136 sits at the heart. Around it, the cleared cavity, the region where stellar winds have blown the gas outward. Beyond that, the dense ring of compressed gas where the winds have piled up material, a shell, like the shock wave expanding outward from an explosion. And in that shell, new stars forming, triggered by the compression, a whole generation of stars being born in response to the previous generation. Concentric rings of star formation, like ripples from a stone dropped in water, but each ripple is a ring of new suns. Astronomers call this process sequential star formation, or triggered star formation. One generation of massive stars triggers the formation of the next. It is a cascade, a chain reaction. The first stars form perhaps triggered by a supernova shockwave or by the tidal forces of a galactic interaction. Those stars blow stellar winds and eventually explode. Their winds and shock waves compress the surrounding gas. New stars form in the compressed gas. Some of those are massive. They blow their own winds. They compress more gas, more stars, and on a chain reaction of creation, propagating through the cloud, star after star, generation after generation. The Tarantula Nebula is not just a star-forming region. It is a demonstration of how the universe bootstraps its own complexity, how each step in the process enables and triggers the next, how creation is not a single event but a cascade. There is something here that I keep coming back to. The idea that violence and creation are not opposites in the universe. Here, they are the same thing. The radiation that is destroying the edges of the pillars is also triggering new star formation. The stellar winds that are blasting cavities in the nebula are also compressing gas elsewhere. The supernovae that scatter the contents of massive stars are also seeding the next generation of molecular clouds. Destruction enables creation. Violence propagates structure. The most creative region in our cosmic neighborhood is also the most violent. I don't know what to do with that, philosophically, but I find it true. And I find it in the context of lying still in the dark, listening, breathing, somehow comforting, not because violence is good, but because nothing is purely destructive. Everything feeds something. Everything becomes something else. The end of one thing is the raw material for the next. Other eyes, other galaxies, the Tarantula in context. The Tarantula Nebula is remarkable, but it is not unique in the universe. In the early universe, when galaxies were young and full of gas, and the rate of star formation was orders of magnitude higher than today, regions like the Tarantula were common. Perhaps the dominant mode of star formation. We can see those ancient starburst galaxies when we look at very distant galaxies, galaxies whose light left them billions of years ago. When the universe was young, we see galaxies blazing with star formation, entire galaxies glowing blue-white with the light of newly formed massive stars. Galaxies where the star formation rate is hundreds or thousands of times higher than in the Milky Way today. Some of the brightest objects in the universe are starburst galaxies. Places where a galaxy collision, a gas-rich environment, a gravitational interaction has triggered furious star formation across an entire galaxy. The Tarantula Nebula, vast and violent as it is just a small region of a dwarf galaxy. Our dwarf galaxy. In the early universe, there were whole galaxies doing what the tarantula is doing on a far larger scale. The antennae galaxies, two spiral galaxies currently colliding about 65 million light years away, are creating starburst regions as the collision compresses their gas clouds. Where the galaxies overlap, thousands of new star clusters are forming, regions of star formation far exceeding anything in our galaxy. The collision is violent. Tidal forces are pulling the galaxies apart even as gravity pulls them together. Stars that were in orderly orbits are being flung into new trajectories. Giant molecular clouds are being compressed. And in the chaos of the collision, new stars, billions of them. The universe making something from the wreckage of a collision. The way the moon was made from the wreckage of a collision, the way life might be made from the wreckage of an extinction, the universe has a pattern. It takes the broken and builds something new. The Milky Way itself was built this way. Every merger, every accretion of smaller galaxies over 13 billion years has added material, stars, gas, dark matter to what we live in now. The Milky Way we live in is the accumulated result of billions of years of collisions and mergers and star formation. It is not pristine. It is not simple. It is a patchwork, a complex, layered history of violence and creation. And somewhere in that history, perhaps in an ancient starburst event, long forgotten, the stars that made our sun were forged. The material that became the sun, the material that became the earth, the material that became you, forged in something that may have looked billions of years ago, something like the Tarantula Nebula. The question that remains: life, violence, and the unlikely universe. Is there life in the Tarantula Nebula? Almost certainly not. The environment is too violent, the radiation too intense, the timescales too short. The most massive stars in R136 live for a few million years. Life on Earth took hundreds of millions of years to develop even to the level of single cells, billions of years to reach complexity. The stars of the tarantula won't last long enough. The planets, if they can form, won't survive long enough. The Tarantula Nebula is not a place for life. It is a place for making the material from which life elsewhere and later might arise. But there is something I find remarkable about even asking the question, about even thinking it. We are right now organisms that arose on a small rocky planet orbiting an ordinary star in the quiet suburbs of the Milky Way. We have existed as a species for about 300,000 years. We have had modern science for about 400 years. And in those 400 years, in that fraction of a moment in the history of the universe, we have learned to detect the light from a nebula 170,000 light years away. We have learned to analyze that light, to determine its chemical composition, to map its structure, to understand the processes happening within it. We have sent a telescope into space, a telescope that can see infrared light from objects whose photons have been traveling for billions of years. And we have pointed it at the tarantula, and we have seen it, really seen it, in detail from an insignificant planet in a quiet corner of a medium-sized galaxy. We looked across 170,000 light years, and we understood what we were looking at. I find that more remarkable than anything in the nebula itself. Not the size of the nebula, not the violence of R136, not the mass of R13601, the fact that something that arose from the same processes, the same star formation, the same element synthesis, the same planetary formation, the same chemistry, the same biology, looked back at those processes and understood them. The universe made something that could look at the universe and comprehend it. That is the most extraordinary fact in this entire documentary. Not in the tarantula. Here, in you, the thing that is lying still in the dark right now. Breathing, listening, understanding the atoms in your body, the hydrogen, the carbon, the oxygen, the iron, pass through stars before they pass through you. Some of them may have passed through regions not unlike the Tarantula Nebula. Some of them were made in supernovae like SN 1987A. Some of them have been cycling through the universe for 13 billion years. And now they are temporarily, for a few decades, organized into a pattern complex enough to be aware of itself, aware of the universe, aware of the Tarantula Nebula, aware that the universe is old and violent and creative and vast, aware that all of this, every nebula, every star, every supernova, every galaxy is somehow connected to the quiet rise and fall of your breath right now, the long quiet. What the tarantula will become, the Tarantula Nebula will not always be what it is now. Nothing is permanent. The massive stars of R136 will burn for another few million years at most, and then they will begin to die. The most massive first. R136 or 1, perhaps only 1 or 2 million years from now, will exhaust its fuel. Its core will collapse. It will explode in a supernova. Not as close to us as SN 1987 AR 136 is deeper in the Large Magellanic Cloud, but close enough, detectable, visible, perhaps, to the naked eye, if there's still eyes to see it. After the massive stars die, the star formation will slow. The radiation and stellar winds that have been driving the process will diminish. The gas of the nebula, already being dispersed, will continue to scatter. What will be left, eventually, is a star cluster, like R136 already is. A cluster of stars without the surrounding nebula. No more gas, no more formation, just the stars, orbiting their common center of gravity, slowly drifting apart over billions of years as the cluster dissolves. The nebula will be gone, the violent, creative phase will be over, but the stars it made will remain. They will scatter through the Large Magellanic Cloud. Some will be flung out by gravitational interactions, runaway stars, shooting through intergalactic space. Most will settle into orbits in the LMC. The less massive ones, the ones like our Sun, which are forming even now in the quieter regions of the nebula, will burn for billions of years. Long enough for planets to form, long enough for chemistry to begin, long enough for something to arise on those planets and look up, and perhaps see the remnant glow of the cloud in which they were born, and wonder. The universe is patient. It makes violent things, enormous things, things that burn and explode and scatter themselves across galaxies. And from the scatter, slowly, patiently, over billions of years, it makes quiet things. Rocky planets, liquid oceans, single cells, complex organisms, things that breathe, things that think, things that lie still in the dark, and try to understand. And we do. Not completely, not yet, but we try. And the trying, the reaching towards something vast and unreachable is itself one of the most distinctly human things we do. We are the only things in the known universe that look up and ask why. We are the only things that look at a smudge of light in the southern sky and build instruments to understand it. That is not nothing. That is everything. The silence after the nebula, what it means to look. There is a particular kind of silence that happens after you've really looked at something enormous. Not the silence of emptiness, the silence of fullness, of a mind that has taken in more than it can immediately process and needs a moment, just a moment, to sit with what it has received. You know, the silence, you have felt it at the edge of an ocean, at the top of a mountain. In the moment after a piece of music ends and before the applause begins, in the space between breaths, when something beautiful has just happened and you're not ready for it to be over, that silence is where understanding lives. Not in the words, not in the numbers, in the quiet after. When the Hubble Space Telescope first returned deep field images, long exposures of apparently empty patches of sky, astronomers expected to see a few distant galaxies. What they saw instead was thousands. Thousands of galaxies in a patch of sky so small that if you held a grain of sand at arm's length, the grain would cover it. Each galaxy containing hundreds of billions of stars. Each star potentially surrounded by planets. The image was released, and something happened that does not often happen in science. People wept, not from sadness, from the particular overwhelm that comes from suddenly understanding how large the container is, how small the room you had been imagining, how much more there is. There is a name for this feeling. The philosopher Edmund Burke called it the sublime, the experience of something so vast it exceeds your capacity to contain it, and in that excess produces a kind of awe that is almost indistinguishable from fear. But it is not fear, not exactly. It is the feeling of your mental model of the world expanding suddenly, painfully, beautifully to accommodate something it had not previously made room for. The Tarantula Nebula produces this feeling. The Hubble Deep Field produces this feeling. The night sky, really looked at, produces this feeling. And I think that feeling is important, not just aesthetically. Cognitively, when you feel the sublime, something changes in how you hold the world. The ordinary concerns of ordinary days become briefly smaller. Not unimportant, but smaller, appropriately smaller, scaled correctly against the actual size of things. And from that scaling, from that momentary correct perspective, something clarifies. What matters? What is fleeting? What is permanent? What you are part of. The dark between the stars, what space actually is. Most of space is nothing. This seems obvious. It is not. The nothing of space is not the nothing of an empty room, a room still filled with air, with dust motes, with light, with the hum of a refrigerator somewhere in the building. The nothing of interstellar space is almost nothing, almost. In the densest part of the Tarantula Nebula, in the star-forming molecular clouds, there are perhaps 10,000 molecules per cubic centimeter. 10,000 sounds like a lot. In the air around you right now, there are approximately 27 million billion molecules per cubic centimeter. The densest part of the nebula is, by earthly standards, the most perfect vacuum imaginable. And the spaces between the stars, the truly empty interstellar medium, are far emptier than that. Perhaps one atom per cubic centimeter, and between galaxies, in the vast voids that separate galaxy clusters, perhaps one atom per cubic meter or less. The universe is almost entirely empty. The matter that makes stars, planets, oceans, trees, animals, you is a thin scattering of structure in an immensity of nothing. And yet, look up on a clear night, the sky is full of light. Every point of light is a sun. Many of those suns have planets. The light is so abundant it obscures the darkness behind it. We evolved on a planet bathed in the light of a single star, surrounded by the light of billions more. We are not the empty part. We are the rare, extraordinary, structured part. The part where the matter found other matter and held on. Where gravity drew things together against the general tendency toward dispersal. Where complexity accumulated. There is no guarantee that complexity had to accumulate. No law that required it. The universe could have been a perfect, featureless gas, hydrogen, expanding uniformly into an expanding space, never clumping, never forming stars, never making anything. The tiny fluctuations in the density of the early universe, quantum fluctuations, amplified by inflation, are what seeded the structure. The first unevennesses, the first places where there was fractionally more matter than average. Gravity did the rest, slowly pulling the matter together over hundreds of millions of years into the first stars, into the first galaxies, into everything. You are the result of a quantum fluctuation, a tiny unevenness in the density of the early universe, amplified over 13.8 billion years into a mind capable of understanding what a quantum fluctuation is. I do not know what to do with that, except to find it extraordinary. The first stars, before everything, the first stars were different. We have never seen one, not directly. They formed, lived, and transformed before any telescope existed, before Earth existed, before the sun existed. But we can reconstruct them from theory, from the chemical signatures they left in later generations of stars, from the oldest objects we can observe. The first stars formed from almost pure hydrogen and helium, no carbon, no oxygen, no iron, no dust, just the lightest elements, the ones made in the Big Bang, falling together under gravity in the young universe. Without heavy elements to help cool the gas, the first molecular clouds were warmer than clouds today. Warmer clouds resist gravitational collapse more effectively. The result, the first stars were enormous. Estimates suggest typical masses of hundreds of solar masses, perhaps thousands, monsters blazing with an intensity that makes R136 a one-look moderate. They would have lived for only a few 100,000 years. In that time, they would have poured out so much ultraviolet radiation that they began to reionize the gas around them, stripping electrons from the hydrogen that had, for hundreds of millions of years, been neutral. This period, called the Epoch of Reionization, is one of the great phase transitions of the universe. The moment when the universe went from a dark, neutral fog to a lit, ionized place. The first stars switched on the lights, and then they transformed, each one seeding the universe with heavy elements that had never existed before. Carbon, oxygen, the first carbon in the universe, scattered from the first stellar transformations, beginning the long chain that eventually leads to chemistry, to molecules, to biology, to you. The first stars never had planets. There was no material to make planets from no rock, no metal, no dust of the right composition. They blazed and transformed alone into an empty universe, making it, for the first time, possible for something else to follow. Unwitnessed, unobserved, no eyes to see them, no mind to wonder at them, just the physics, working as it always has, as it always will. The weight of light, what photons carry. Every photon that reaches your eye carries information, not metaphorically. Literally, a photon of a specific wavelength tells you the temperature of the object that emitted it. The spectrum of photons tells you the chemical composition. The Doppler shift of the spectrum tells you whether the object is moving toward you or away, and how fast. The polarization of the light tells you about magnetic fields. The timing of variations in brightness tells you about size, about orbits, about the presence of companions. Light is not just illumination. Light is a message. From every object in the universe, a constant stream of messages, encoded in wavelength and timing and polarization, and we in the last few centuries have learned to read them. When astronomers point a spectrograph at a star and spread its light into a rainbow, they see dark lines, absorption lines. Each line corresponds to an element in the star's atmosphere absorbing photons of a specific wavelength. Each element has a unique fingerprint, a unique set of wavelengths it absorbs. Hydrogen has its lines, helium has its lines. Iron, calcium, sodium, magnesium, each one a unique pattern. And by reading those patterns, we can tell you exactly what a star is made of. From here, without going there, without touching it, without anything physical passing between us and the star. Just light, just the photons that left the star years or centuries or millennia ago and happened to reach your telescope. We are reading the universe through its light, and the universe is extraordinarily talkative. Every object radiating constantly, every photon carrying its payload of information. The universe has been sending messages since the first stars lit up. We have only just learned to receive them, and we are still learning. Every new wavelength range, we open up radio, infrared, ultraviolet, X-ray, gamma ray, reveals a new layer, a new set of messages, a new way the universe is speaking. We have been, for most of human history, nearly deaf to it. And now, gradually, we are learning to hear the gravity of things, the force that makes everything. Gravity is the weakest of the fundamental forces. This seems wrong. It seems impossible. Gravity pulls you to the earth, holds the moon in orbit, keeps the planets around the sun, holds the galaxy together. How can it be the weakest force? And yet, the electromagnetic force between two protons is approximately 10 to the power of 36 times stronger than the gravitational force between them, a number with 36 zeros. Gravity is that much weaker, and yet it dominates the universe at large scales, because it has a crucial property that the other forces do not. It has infinite range, and it is always attractive. The electromagnetic force can be attractive or repulsive. Positive charges repel positive charges, attract negative charges. At large scales, matter is electrically neutral, equal amounts of positive and negative charge, and the electromagnetic forces cancel out. Gravity has no negative charge. There is no anti-gravity. Every mass attracts every other mass, always, over any distance. No matter how small the force, it never stops. And over cosmological distances, all those tiny attractive forces add up to something that can hold galaxies together, that can curve the path of light, that can collapse a stellar core in less than a second. Gravity is patient. Gravity accumulates. Gravity wins. The Tarantula Nebula, the star formation, the stellar winds, the compression, the collapse, all of it is gravity's project. Gravity found the gas. Gravity pulled it together. Gravity compressed it until it burned. Gravity is the architect. Everything else, the light, the heat, the radiation, the chemistry, is what happens inside the structures that gravity builds. When you look at the web images of the tarantula and see the pillars of gas and the clusters of stars and the intricate structure of the nebula, you are looking at the art that gravity makes from almost nothing over billions of years, slowly, without intention, without design, just the patient accumulation of the weakest force, building everything, the elements and their journeys, a periodic table written in stars. The periodic table is a map of stellar history. Every element beyond hydrogen and helium has a story, a specific origin, a specific astrophysical process that made it. Lithium, the lightest metal, was made partly in the Big Bang and partly in cosmic ray spallation, high-energy particles shattering heavier nuclei into lighter fragments in the spaces between stars. Carbon, the backbone of life, forged in the triple alpha process in stellar cores. Nitrogen, the dominant gas in the air you are breathing, the element in the amino groups of every protein in your body made in intermediate mass stars, in the CNO cycle, a fusion process that cycles through carbon, nitrogen, and oxygen. Oxygen made in massive stars, scattered in their final moments, neon, sodium, magnesium, deeper layers of stellar fusion. Silicon, the dominant element in the Earth's crust, the material your world is built from, made in the silicon burning phase of massive stars in the last few days of their lives. The last few days, silicon burning lasts only days before the core transforms. The silicon in the rocks beneath your feet was made in the final days of a massive star. Calcium in your bones, in the chalk that makes white cliffs, in the shells of marine creatures made in massive stars and scattered in their final moments, the calcium in your skeleton was once inside a star. Iron, the end of the fusion chain made as the core transforms. Copper, zinc, germanium made in the quiet, ongoing processes of stellar evolution over billions of years. Gold, silver, platinum, the heaviest, most precious metals, not made in normal stellar fusion, not made in ordinary stellar moments, made in the most powerful events the universe produces. The meeting of neutron stars, when two ancient stellar cores, each one the mass of the sun, concentrated into a sphere 20 kilometers across, draw closer together over millions of years and finally meet. In the milliseconds of that meeting, the conditions are remarkable enough to produce the heaviest elements: the gold in a ring, the silver in a mirror, the platinum in a catalyst, made in milliseconds, in a meeting between two ancient stars scattered into the galaxy, eventually concentrated in the solar nebula, eventually found in riverbeds, eventually shaped by human hands into objects of beauty and value. Every piece of gold on Earth is the product of a neutron star meeting that happened before the sun was born. Every wedding ring carries the memory of ancient stars, made beautiful by time. The Milky Way from outside, we have never seen the Milky Way from outside. We are inside it. Embedded in one of its spiral arms, the Orion arm, about 26,000 light years from the center, we cannot step outside and look back. We cannot take a photograph from above. Everything we know about the large-scale structure of our galaxy, the number of spiral arms, their shape, the size of the central bulge, the extent of the disk, we have learned by inference, by looking in all directions, by measuring distances and velocities, by building a map from within. It is like trying to draw a map of a city you have never left, using only the view from your window. But we have done it with remarkable precision. The Milky Way is a barred spiral galaxy, about 100,000 light years across, a flattened disk, perhaps 1,000 light years thick in most places, with a central bar of stars and two major spiral arms winding outward, and a central bulge, a dense concentration of mostly older, redder stars surrounding the very center, where something extraordinary exists. The disk contains most of the young stars. The spiral arms, traced by the blue-white light of massive young stars, by the glow of nebulae, by the emission of radio waves from hydrogen clouds, are where star formation is most active: the Orion Nebula, the Eagle Nebula, the Lagoon, the Carina, all in the disk, all in or near the spiral arms. And surrounding all of this, extending far beyond the visible disk, is the dark matter halo, an invisible structure of unknown material, perhaps 10 times the mass of all the visible stars combined, providing the gravitational scaffolding that keeps the galaxy together, that keeps the outer stars from drifting into intergalactic space. We know it is there because of what would happen without it. Without the dark matter halo, the rotation of the galaxy makes no sense. The outer stars move too fast, far faster than they should, if the only gravity acting on them came from the visible matter. Something invisible is holding them in. Something we have never detected directly, something we do not understand. The Milky Way, the galaxy we live in, the only galaxy we have ever called home, is mostly made of something we cannot see, cannot measure directly, and do not understand. The known universe is the small part, the lit part, the part we can read. Most of our galaxy, most of the universe, is written in a language we have not yet learned. Sagittarius, our star, the heart of the galaxy, at the center of the Milky Way, 26,000 light years away, is something extraordinary. We call it Sagittarius A star, a supermassive black hole, 4 million times the mass of the Sun, concentrated into a region smaller than the orbit of Mercury. For decades, we knew it was there. We could see the stars orbiting it, moving in tight, graceful ellipses around an invisible point, reaching speeds of thousands of kilometers per second at their closest approach. Nothing but an enormous mass could produce such orbits, an invisible mass, a mass that emitted no light, a gravitational object so dense that not even light could escape from within it. In 2019, the Event Horizon Telescope, a network of radio telescopes spanning the entire Earth, working together as a single instrument, produced the first image of a black hole. Note Sagittarius A star, the black hole at the center of the galaxy M87, a monster 6.5 billion times the mass of the Sun, a glowing ring of hot gas swirling around the dark center, the shadow of the event horizon, the edge of the point of no return. And in 2022, after years of additional work, the same collaboration produced the first image of Sagittarius A star, our own, the one at the center of our galaxy, a glowing ring, a dark shadow, the same shape, the same physics, Betuchs. Sagittarius A star is, at the moment, relatively quiet. It flares occasionally, bursts of X-ray emission, moments of increased activity, but compared to the active galactic nuclei of other galaxies, it is almost dormant. Other galaxies have supermassive black holes that are actively consuming gas and dust in enormous quantities, producing jets of plasma that extend for millions of light years, outshining entire galaxies. These are quasars, the most luminous, persistent objects in the universe, powered by gravity, by the energy released as matter falls toward the event horizon and heats up and radiates before crossing it. Our black hole is not doing that. Not now. But it has evidence in the gas above and below the galactic plane suggests that a few million years ago, Sagittarius A star was active, enormously active, producing a pair of enormous bubbles of hot gas, the Fermi bubbles detected by the Fermi Gamma Ray Space Telescope, extending tens of thousands of light years above and below the galactic plane. The remnants of an ancient outburst, a moment when the center of our galaxy blazed. We were not there to see it. By the time it happened, the light took millions of years to reach us. But the bubbles remain, evidence of a violence at the center of our galaxy. Long past, still written in the structure of the gas. The local group, our family of galaxies, the Milky Way is not alone. It belongs to a family, a cluster of galaxies bound together by gravity, orbiting each other, occasionally interacting, called the local group. About 50 galaxies, most of them small, dwarf galaxies, irregular collections of a few billion stars, orbiting the two dominant members, the Milky Way and Andromeda. Two large spiral galaxies separated by about 2.5 million light-years, both surrounded by their retinue of dwarf galaxy satellites in gravitational terms. The Magellanic Clouds, the large and small, are satellites of the Milky Way. The Tarantula Nebula is in the large Magellanic Cloud. The most active star-forming region in our cosmic neighborhood is happening in one of our satellite galaxies. In our galactic family, and Andromeda, the other great spiral, the largest galaxy in the local group, is approaching, moving toward us at approximately 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will collide. Not a collision in the ordinary sense. The stars are so far apart that few, if any, stars will actually collide. But the gas clouds will collide. The tidal forces will distort both galaxies beyond recognition. Star formation will surge, triggered by the compression of gas clouds. A starburst event, perhaps producing regions like the Tarantula Nebula, perhaps larger. The merged galaxy, sometimes called Milkomeda, will be a large elliptical, the spiral arms gone, the disk gone, a roughly spherical cloud of stars orbiting each other in complex patterns, no preferred plane, no rotation, just stars, billions of them in a new configuration. The sun, if it still exists, will likely be thrown into a different orbit, perhaps flung to the outer reaches of the merged galaxy. The night sky will look nothing like it does now. The familiar constellations gone, replaced by a sky dominated by the diffuse glow of the merged galaxies. A different sky for different eyes. If there are eyes to see it, the cosmic web, the largest structure, zoom out further, beyond the local group, beyond the nearest galaxy clusters, beyond the superclusters, to the largest scales, to the scale at which individual galaxies are too small to see. At this scale, the universe has a structure, a web, the cosmic web, filaments of dark matter and gas and galaxies, stretching for hundreds of millions of light years, connecting at nodes dense clusters of thousands of galaxies. Between the filaments, vast voids, nearly empty spaces, hundreds of millions of light years across, containing very few galaxies. The universe at the largest scale looks like a sponge, or a form, or a neural network. The resemblance to neural networks is not lost on anyone. The cosmic web and the network of neurons in the human brain share structural similarities, branching, connecting, forming nodes of density. This is probably a coincidence. Or perhaps just a feature of networks in general, the same mathematical principles governing very different physical systems. But it is striking. The universe, at its largest scale, looks something like the organ that is thinking about it. The filaments of the cosmic web are not empty. They contain gas, warm, diffuse gas, and streams of galaxies moving along them, drawn by the gravity of the nodes at their ends. Galaxies do not move randomly through the universe. They move along the web, along the filaments, toward the nodes. Our local group is moving toward the Virgo cluster, a dense cluster of thousands of galaxies, 40 million light years away. We will not reach it. The expansion of the universe will prevent it. But we are aimed at it, moving toward it, part of the flow, part of the web, the expansion, what dark energy is doing. The universe is expanding, not into anything, not into empty space that was already there. Space itself is expanding. The distance between distant galaxies is increasing not because they're moving through space, but because the space between them is growing. Edwin Hubble discovered this in 1929. He noticed that distant galaxies are receding, their light is redshifted, stretched to longer wavelengths by the expansion of the space the light traveled through. And the further the galaxy, the faster the recession. Not because more distant galaxies are moving faster, because more space is expanding between us and them. More space to grow. The expansion was expected after Einstein's equations of general relativity to be slowing down. Gravity, pulling all the matter in the universe toward all the other matter, should be decelerating the expansion like a ball thrown upward, slowing under gravity. In 1998, two teams of astronomers using distant supernovae as standard candles to measure distances across the universe found something that shocked the entire field. The expansion is not slowing down, it is accelerating. The universe is expanding faster over time, not slower. Something is counteracting gravity. Something is pushing the universe apart. We call it dark energy. We do not know what it is. It may be a property of space itself, a quantum energy of the vacuum, an energy that exists in empty space and drives expansion. It may be something else entirely, something we do not have the concepts yet to understand. What we know is this: dark energy makes up approximately 68% of the total energy content of the universe. Dark matter makes up approximately 27%. Ordinary matter, everything we can see, everything we can touch, every star and planet and nebula and person makes up approximately 5%. 5%. We are in the minority. The universe is mostly made of things we do not understand. And the thing we do not understand that dominates dark energy is pushing everything apart, faster and faster. In the very far future, in hundreds of billions of years, the expansion will have carried every galaxy beyond our cosmic horizon. Every galaxy outside the local group will be receding faster than the speed of light, not violating relativity, because it is space expanding, not objects moving through space, and their light will never reach us. The night sky will be empty, except for the merged Milky galaxy, and perhaps a few gravitationally bound companions. Everything else, the billions of galaxies we can see today, will be gone from view, beyond reach, beyond knowledge. A civilization arising in that distant future, if any civilization exists, will look out at an apparently empty universe. They will have no way of knowing that beyond their horizon, thousands of billions of galaxies exist. They will think they are alone. They will be wrong, but they will never know they are wrong. We are fortunate. We live in the early universe early enough that the galaxies are still within sight, early enough to see the cosmic web, early enough to look at the Tarantula Nebula and know what it is, early enough to understand something of where we are. Later arrivals will not have this. We have caught the universe at a moment when it can still be understood, time, what it actually is. We have been talking about time as if we all know what it is. We do not. Time is one of the deepest mysteries in physics. We experience it as a flow, a movement from past to future, from cause to effect. But the equations of physics are mostly time symmetric. They work the same whether time runs forward or backward. The laws of physics, with a few exceptions, do not care which direction time flows. And yet we experience a clear direction. We remember the past. We cannot remember the future. We can influence the future. We cannot influence the past. Why? The best answer we have involves entropy, the second law of thermodynamics. Entropy always increases. Disorder always increases. A cup falls and breaks. It does not spontaneously reassemble. Smoke disperses into the air. It does not spontaneously reconcentrate into the candle. Time's arrow is the direction of increasing entropy. The past was more ordered. The future is less ordered. We move from order toward disorder. And the reason the past was more ordered ultimately is that the Big Bang was an extraordinarily low entropy starting point, almost perfectly smooth, almost perfectly uniform, the lowest entropy the universe has ever had. Everything since has been the slow relaxation of that initial low entropy state. The stars burning, the structures forming, the disorder increasing. Time's arrow is the arrow pointing away from the Big Bang. The past is toward the Big Bang. The future is away from it. We are moving away from the beginning, which means that somewhere in the structure of time itself, the Big Bang is the reason we can remember the past, but not the future. The origin of the universe is the origin of time's direction. We carry the Big Bang in the asymmetry of our experience, in the fact that we know what happened yesterday and do not know what will happen tomorrow. The Big Bang is the reason for memory. The Big Bang is the reason for anticipation. The Big Bang is present in every moment of your experience. Every moment, including this one, consciousness, the most mysterious thing in the universe. We have traveled far tonight, from the Tarantula Nebula through the structure of the universe to the nature of time. But there is one more thing to look at, the most mysterious thing in the universe, more mysterious than dark energy, more mysterious than the origin of the Big Bang, more mysterious than quantum mechanics, consciousness, the fact that there is something it is like to be you, the fact that the universe is not just matter in motion, that somewhere in the arrangement of atoms that is you, experience arises. Subjective experience. The redness of red, the pain of pain, the quiet of this moment, the feeling of listening, the sense of understanding. We have no idea why this happens. We can describe the neural correlates of consciousness, the brain states associated with different experiences. We can trace the processing, the input, the integration, the output, but we cannot explain why any of it feels like anything, why there's experience at all, why it is not all just processing in the dark. Some philosophers and scientists think consciousness is a fundamental feature of the universe, not something that emerges from complex arrangements of matter, but something that is present in some form at some level wherever there's information processing, a property of reality as basic as mass or charge. Others think it will eventually be explained entirely in physical terms. that once we understand the brain well enough, the mystery will dissolve. That what feels like a profound mystery is just the strangeness of a complex system looking at itself. We do not know. We do not know if consciousness is common in the universe or rare. We do not know if it exists anywhere else. We do not know if the universe is full of experience, full of things it feels like something to be, or if the awareness happening in your mind right now is one of the rarest things in existence. We are looking at the Tarantula Nebula from the inside of a mystery. The observer is as mysterious as the observed. And perhaps that is the most humbling thing of all. The universe is vast and old and mostly dark, and somewhere in it, in a thin film of biology on a small rocky world, something happened. Something noticed. Something understood. Something asked why, and still does not know the answer, and asks anyway. The long sleep of matter, before life and after. For most of the universe's history, nothing was alive. For the first several 100 million years, there were no planets, no chemistry, no oceans, just gas. And the first stars blazing in the dark. And for most of what followed, most of the 13.8 billion years, the matter that would eventually become life was doing something else. Being a star, being a nebula, being a molecular cloud, being part of an ocean on a world where conditions never quite aligned for life to begin. The matter that is you right now has been through many forms. It does not know it was a star. It does not remember the nebula, but it went from the hot plasma of the early universe to the core of a massive star, from the stellar transformation to the interstellar medium, from the gas cloud to the solar nebula, from the solar nebula to the young Earth, from the rocks of the early Earth to the ocean, from the ocean to the first cells, from the cells to everything that followed, 4 billion years of biological evolution, of life experimenting with forms, of chemistry becoming more complex, of simple organisms becoming complicated ones, of complicated ones becoming conscious, of consciousness becoming curious, of curiosity reaching out to the stars it came from. You are matter that became briefly alive, briefly aware, looking back at the matter it came from. The looking back is the extraordinary part. The matter was there before the looking. It will be there after. But right now, in this thin sliver of time, it is looking and finding it beautiful and trying to understand what we owe the dark, a gratitude for emptiness. The darkness between the stars is not absence. It is the space in which things become visible. Without the dark, there is no contrast. Without the contrast, there is no seeing. The stars are visible because of the dark surrounding them. The nebulae glow because of the dark that frames them. The structure of the universe, the web, the filaments, the clusters, is only visible because the voids between them are genuinely empty. We owe the dark something, not sentimentally. Literally, the silence in a piece of music is not the absence of music. It is part of the music. The pause that makes the note meaningful. The empty measure that makes the full one sing. The universe works the same way. The emptiness is part of the structure. The structure requires the emptiness. And we here are in the lit part, the rare part, the warm, dense, structured, carbon-rich, water-soaked, biology having, consciousness-producing part. The ordinary matter part, the 5%, and the dark surrounds us completely. The dark matter, the dark energy, the void between the galaxies, the silence between the stars, all of it necessary, all of it part of the same thing, the same universe, the same story, and we are not apart from it. We are in it, made of it. reading it, wondering at it from the inside, in the small lit room of our own awareness, surrounded by an incomprehensible dark that is somehow home, the return coming back to the room. And now, slowly, without rushing, we come back from the Tarantula Nebula, from the first stars, from the collision of neutron stars that made the gold in the world, from the center of the Milky Way, from the cosmic web, from the edge of what we can see, from time itself, from the mystery of consciousness looking at itself. We come back to this room, to this body, to this breath. The breath that is happening right now is steady, quiet, the same breath that has been breathing since before you were aware of breathing tonight. The body that is lying still, supported, the weight of it distributed into the surface beneath you, heavy in the way bodies are heavy when they are truly at rest. The room around you, its particular quiet, its particular dark, its particular temperature, the sounds, if there are sounds settling into the background, into the texture of the silence rather than interrupting it. You are back, though you never left. You were here the whole time. Your body here, your breath here, your atoms here, the same atoms that were in stars, in nebulae, in the young earth, in the ocean, in every living thing that came before you. Here, in this room, for this night, doing the most ordinary and necessary thing, resting. The universe does not need you to do anything right now. It has been managing for 13.8 billion years. It will continue. The Tarantula Nebula is still forming stars. The Milky Way is still turning. Sagittarius A star is still there at the center, patient and quiet. The cosmic web still holds its structure. The atoms still move according to the laws they have always followed. All of it continuing without effort, without attention. The universe requires nothing of you tonight, except what you are already doing. Being here, breathing, being the part of the universe that briefly noticed itself. That is enough. That has always been enough. The last light, what we know and what we don't. The James Webb Space Telescope can see objects whose light left them when the universe was only a few 100 million years old. We can see almost to the beginning, almost to the moment when the first stars lit up and filled the universe with the first light that was not the glow of the Big Bang itself. We are close to the edge of what is knowable. Not because of the limits of our technology, though those limits exist, but because of the limits of physics itself. Beyond a certain point, beyond the distance that light has had time to travel since the Big Bang, there is no information. Not because there's nothing there, but because the light from there has not reached us yet. The observable universe is a sphere of knowledge, defined not by what is out there, but by what we can possibly receive. Everything outside the sphere is, in principle, unknowable. Not now. Not ever, regardless of how sophisticated our instruments become. We are inside the bubble of knowability, regardless of how sophisticated our instruments become. We are inside the bubble of knowability, looking outward to its edge. Beyond the edge, perhaps forever the universe continues. We will never know how far. We will never know what is there. We will never know if the laws of physics are the same. We will never know if there are other regions of space with different constants, different forces, different histories. We do not know if what we can see is representative. We do not know if we are in a typical part of the universe. We do not know if our universe is the only one. We do not know if there are others with different properties, different outcomes, whether the multiverse is real, whether the constants of our physics, the strength of gravity, the charge of the electron, the mass of the proton could have been different, whether there are configurations of the laws of nature that would allow no structure, no stars, no chemistry, no life, and whether in some deep sense we cannot yet articulate the universe we find ourselves in had to be the way it is, for us to be here to find it. These are not questions science has answered. They are questions science is sitting with. And perhaps the most important thing about them is not their answers, but the fact that we can ask them, that the universe produced in one small corner something capable of reaching the limits of its own knowledge, and looking out and wondering what is beyond, and not knowing, and asking anyway. The spiral arms let us stay with the galaxy for a while longer. The spiral arms of the Milky Way are not solid structures. This is one of the most commonly misunderstood things about spiral galaxies. The arms are not like the spokes of a wheel fixed, rotating with the galaxy as a rigid unit. They are more like a wave. A wave moving through water does not carry the water with it. The water molecules move up and down as the wave passes. The wave is a pattern, a region of compression moving through a medium. The spiral arms are something like this. A density wave, a region where the gravitational conditions favor the accumulation of gas and dust, moves through the galaxy. As gas clouds enter the arm, they are compressed. The compression triggers star formation. New stars ignite. The most massive ones burn brilliantly and briefly, illuminating the arm with blue-white light before dying in a matter of millions of years. The arm glows because of these short-lived massive stars, not because the same stars are always there, but because the conditions in the arm constantly produce new ones. The spiral arms are regions of star birth, moving slowly through the galaxy, leaving behind the fading remnants of the stars they have already made. Our sun passed through a spiral arm long ago. It is currently between arms in a quieter region, a minor spur, not at the center of activity. Perhaps that is why the solar system has been relatively stable for 4.5 billion years. The violent star-forming regions of the spiral arms are not a peaceful place to grow a planet. We may be here, in part, because we are between the waves. Dark matter. We have mentioned dark matter several times now. It deserves its own space. Dark matter is the name we give to whatever is providing the missing gravity in the universe, the gravity that holds galaxies together, the gravity that shapes the large-scale structure of the cosmos, the gravity that accounts for the difference between what we can see and what the mathematics requires to be there. It is called dark, not because it is black, not because it absorbs light, but because it does not interact with light at all. Normal matter, the matter you are made of, the matter stars are made of, the matter planets and dust and gas are made of, interacts with electromagnetic radiation. It absorbs light, it emits light, it reflects light. Dark matter does none of these things. It passes through normal matter as if normal matter were not there, through stars, through planets, through you, right now, in uncountable quantities without leaving any trace. We have never caught it, never isolated it, never held it in an instrument and measured its properties directly. We know it exists because of what it does to the things we can see. The rotation curves of galaxies, the bending of light around galaxy clusters, the large-scale distribution of galaxies across the universe, the growth of structure from the tiny fluctuations of the early universe into the cosmic web of filaments and voids we see today. All of it requires something we cannot see. The leading candidates, weakly interacting massive particles, actions, sterile neutrinos, remain undetected despite decades of extraordinary sensitive experiments. Dark matter may be the most abundant form of matter in the universe, and we do not know what it is. There is something humbling about that, something that puts the achievements of human science in perspective. We can image a black hole 26,000 light years away. We can detect gravitational waves from neutron stars merging a billion light years distant. We can map the cosmic microwave background with extraordinary precision. And we cannot identify the most common form of matter in existence. The universe keeps its deepest secrets carefully. The local group, the Milky Way, does not exist in isolation. It is part of a family, a gravitationally bound collection of galaxies called the local group, approximately 50 to 80 galaxies spread across a region roughly 10 million light years across. The largest members are the Milky Way and the Andromeda Galaxy, two spiral galaxies of comparable size, separated by about 2.5 million light years. Then the smaller spirals, the Triangulum Galaxy, a smaller, looser spiral, the third largest in the local group, and then the dwarfs. Dozens of them, small, irregular, elliptical galaxies containing millions or billions of stars rather than hundreds of billions, orbiting the larger galaxies like satellites. The Magellanic Clouds, visible in the southern hemisphere as two detached patches of the Milky Way, are dwarf, irregular galaxies orbiting our own. The Large Magellanic Cloud contains about 30 billion stars. The small, a few billion. They are close enough that the tidal forces of the Milky Way are slowly pulling them apart. Streams of stars, tidal tails, extend behind them as they orbit, material drawn away by gravity and stretched into arcs across the sky. In the distant future, they will likely be absorbed entirely, consumed by the larger galaxy, their stars scattered through the Milky Way, their identities dissolved. Galaxies, like almost everything in the universe, do not maintain their form forever. Andromeda, and then there is Andromeda, 2.5 million light years away, containing perhaps 1 trillion stars, larger than the Milky Way in extent, though possibly similar in mass, moving toward us, not slowly. At approximately 110 kilometers per second, Andromeda is approaching the Milky Way. The two galaxies are gravitationally bound. They have been drawing toward each other for billions of years. In approximately 4.5 billion years, they will begin to interact, not a sudden impact, not a collision in the way two cars collide. A slow gravitational dance stretching over hundreds of millions of years. The two galaxies will pass through each other. Stars will be flung into new orbits. Tidal tails, great arcs of stars pulled out by gravity, will extend across millions of light years. They will separate, come back together, orbit each other, merge. Over perhaps 2 billion years of interaction, they will become a single galaxy, an elliptical galaxy. No more spiral arms, no more disk, just a vast, diffuse cloud of stars, the combined stellar populations of two galaxies that once existed independently. Astronomers have already named it Milkomeda or Milkdromeda, the galaxy our sun will inhabit when this is done. If the sun still has planets by then, if anything remains on those planets, to look up at what the sky has become. The night sky in 4.5 billion years, for any eyes that might exist to see it, will be extraordinary. The approaching galaxy filling more and more of the sky, then the chaos of the interaction. Stars flung to new positions. New star formation triggered by the compression of gas clouds. A sky unlike anything any eye has ever seen. And then the long settling, the gradual quieting, the new elliptical galaxy cooling into its final shape. The universe transforms everything. Given enough time, the scale of the galaxy, let us try once more to feel the scale. Not just think it, feel it. The Milky Way is 100,000 light years across. If you could travel at the speed of light, the absolute maximum speed the universe permits, it would take 100,000 years to cross it. 100,000 years. The entirety of human civilization, writing, cities, agriculture, science, art spans approximately 10,000 years. To cross the Milky Way at the speed of light would take 10 times the entire span of human civilization, and you cannot travel at the speed of light. Our fastest spacecraft travel at tens of kilometers per second. Voyager 1, the most distant human-made object, travels at about 17 kilometers per second. At that speed, crossing the Milky Way would take approximately 2 billion years. 2 billion years. The galaxy is not a place you can visit, not in any practical sense. Not with any technology we can imagine building. The Milky Way is our home, and it is so vast that we will never see most of it. We are here, in this small corner, in this minor arm, orbiting this ordinary star, looking outward, measuring, inferring, building maps we will never walk, knowing a universe we will never travel. Star formation. Somewhere in the Milky Way right now, a star is being born, not metaphorically, literally, in this moment. In a cold, dense molecular cloud, a region of gas and dust where temperatures approach absolute zero and densities are high enough for gravity to slowly, patiently gather matter. Something is happening. A clump, a concentration, a region slightly denser than its surroundings. Gravity notices. It begins to pull the surrounding material inward, slowly at first, then faster as more mass accumulates and the gravitational pull strengthens. The cloud begins to collapse over hundreds of thousands of years. As it falls inward, it heats up. The gravitational potential energy converts to thermal energy. The temperature at the center rises. It begins to glow, faintly at first, infrared radiation, invisible to the naked eye, and then brighter as the temperature climbs. A protostar, not yet a star, not yet fusing hydrogen, but already gathering mass, already glowing, already beginning to clear the surrounding material with the pressure of its light and heat. Around it, if conditions are right, a disk forms, a flattened disk of gas and dust rotating around the central protostar. In that disk, something extraordinary may happen. Dust grains collide and stick together. Small clumps form. Clumps attract other clumps. Over millions of years, larger and larger bodies accumulate, planetesimals, protoplanets. Eventually, if the process continues long enough, planets, the same process that formed the Earth, the same process that formed every planet we have ever studied, happening right now, around a star that does not yet exist, in a galaxy that contains us both. The death of stars. Every star that has ever existed has died, is dying, or will die. Stars are not permanent, they are processes. Ongoing nuclear reactions sustained by the balance between gravity pulling inward and the pressure of fusion pushing outward. When the fuel runs out, that balance ends. For stars like the Sun, and the vast majority of stars are smaller than the Sun, the end comes gently. The hydrogen in the core is exhausted. Fusion moves to a shell around the core. The outer layers expand. The star becomes a red giant, swelling to many times its original size, cooling as it expands, glowing red rather than yellow-white. For the Sun, this will mean expanding past the orbit of Mercury, past Venus, possibly to the orbit of Earth. Whatever exists on Earth then will face temperatures that make any form of life, as we understand it, impossible. but that is billions of years away. The red giant phase lasts for millions of years. Then the outer layers are shed gently over thousands of years into a shell of glowing gas. A planetary nebula, a brief, beautiful structure, a ring or bubble of illuminated gas surrounding the exposed core. And the core, no longer supported by fusion, no longer undergoing nuclear reactions, is what remains: a white dwarf, dense, hot, gradually cooling over billions of years. A sphere, roughly the size of the Earth, containing most of the mass of a star, so dense that a teaspoon of its material would weigh tons, slowly fading, slowly cooling. In the far future, and timescales far longer than the current age of the universe, it will cool to a black dwarf, a dark, cold remnant, the final state of a star like ours. Silent, invisible, persisting. The silence between stars. We are approaching the end of tonight's journey. Not the end of the subject has no end. There's always more galaxy, always more universe, always another layer of the extraordinary beneath the one you have just understood. But the end of tonight, and so let us settle, let the numbers go quiet. The spiral arms, the dark matter, the ancient stars, the forming stars, the dying stars. Let all of it recede, not forgotten, but resting, filed away, held loosely. You have been somewhere tonight. You have sat in the dark and let your mind move through a structure so large that light takes 100,000 years to cross it. You have considered matter you cannot see, forces you cannot feel, timescales so vast they have no analogy in ordinary experience, and you are still here, still breathing, still occupying this small, warm, particular place in the universe. The Milky Way does not know you're thinking about it. The stars in the spiral arms are not changed by your attention. Sagittarius, a star at the center of the galaxy, 4 million solar masses of compressed spacetime, does not register your awareness of it. But you are changed. Something happens when a mind reaches outward towards something this large, something quiet and difficult to name, a kind of perspective, a softening of the particular urgencies of a particular day. The meeting that went wrong, the message that was not answered, the fear about tomorrow, still real, still yours, but held differently now, placed against a different background. The background of a galaxy 10 billion years old, 100,000 light years across, containing 400 billion stars, moving through a universe of 2 trillion galaxies, expanding outward in all directions at a rate that will eventually carry most of it beyond any possible contact. Against that background, things shift, not disappear, not stop mattering, shift, find their actual size. The return, let your breathing slow now. Feel the weight of your body against whatever is supporting it, the mattress, the pillow, the particular arrangement of the physical world that is, tonight, your corner of the universe. You are made of elements forged in stars. The calcium in your bones, once in a star. The iron in your blood, made in a stellar core. The oxygen in your lungs. The carbon in every cell, stellar in origin. Ancient, forged in fire, and scattered across space, and gathered by gravity and assembled over billions of years into the shape of you. You are not separate from the galaxy you have been thinking about. You are made of it. The Milky Way is not out there while you are in here. There is no boundary. The atoms that make up your body were inside the galaxy long before they were inside you. They will be inside the galaxy long after. You are a temporary arrangement, a brief, conscious, wandering concentration of matter that the universe has produced in this particular corner, at this particular moment. That is not a small thing. That is, in fact, the most remarkable thing we know of. The last stars, let the images come and go now. The spiral arms, turning slowly. The dark matter halo, invisible, vast, patient. The central region, dense with ancient stars. The star-forming regions, glowing faintly in the dark. Somewhere in the galaxy, a star is completing its long life, expanding gently, beginning the process that will, over millions of years, return its material to the space between stars, where it will drift and cool and wait until gravity gathers it again into something new. Nothing is lost. Everything returns. The galaxy is a cycle, has always been a cycle. Stars forming from clouds, clouds forming from the remnants of stars. The same matter used and reused over 10 billion years. You are part of that cycle. The atoms in you have been through this before. They will go through it again. Long after tonight, long after everything you know, long after the sun has become a white dwarf and the earth has been returned to the elements from which it came. The atoms will still be there, part of the galaxy, part of whatever the galaxy becomes. The breath, right here, right now, the breath, still here, steady, patient, in and out, the oxygen entering your lungs made in massive stars, scattered by stellar transformation, drifting through the interstellar medium for millions of years, eventually incorporated into the solar nebula, into the early Earth, into the atmosphere, into this room, into this moment, into you. The carbon dioxide leaving the carbon in it forged in stellar cores, the same carbon that is in every living thing that has ever existed on this planet, cycling through the biosphere, through the atmosphere, through you. Every breath a participation in a cycle that is billions of years old. Every breath a connection to every living thing that has breathed before you. Every breath a small act of continuation. The earth turns, slowly, carrying you through the dark. Toward the light of the sun, a medium-sized star, 4.6 billion years old, in the quiet suburbs of the Milky Way, burning hydrogen into helium at its core, as it has for all of human history and will for billions of years more. Our star, the only one we have ever known, still there, on the other side of the planet, waiting for morning. And somewhere 170,000 light years away, the Tarantula Nebula continues its work. Stars forming in the dark clouds, 800,000 of them, right now, as you breathe, as you rest, as you let the thoughts slow, and the images fade, and the numbers dissolve into something simpler, something quieter, something that does not need to be understood to be true. The universe is old. You are made of it. You are briefly aware, and tonight that awareness is soft and still and almost ready to let go, to rest, to do the thing that all living things do, that all living things have always done, under the same stars, beneath the same dark, with the same breath. In and out, the tarantula burns, the stars are born, the galaxy turns, and you, here, now, sleep.